Okay, thank you very much. So the last talk will be on something called post-CDH descent. And so this actually goes back to an idea of Matthew.
I want to correct this.
Okay.
There were earlier papers of Krishna and Weibel where they really... I mean cancelled. No, but really. I mean, to be fair, earlier papers of Krishna and Weibel where they really... Maybe Srinivas too, where they really do some things. I don't know if they're not really hyping. I think really Krishna deserves a lot of... I think Krishna deserves to be underlining this. Because he has a series of papers where he really looked at...
Okay, thanks. Maybe I should have asked before. Okay, sorry, but I mean he will come back at some point. Okay, so the situation is as follows. So let me recall. Yesterday I briefly defined what an abstract blow-up square is. So I think I changed notation now a little bit. So this is for now just a square like this. Z and X. Let's call this P. So this is a Cartesian. So okay, this is an abstract blow-up square. Abstract blow-up. And by definition, this means first of all it's Cartesian. So let's say here of schemes. So usual, some classical schemes. So i.e. it's Cartesian. Then this map P is proper. Okay, so these are closed immersions. This is what these symbols here should indicate. And if you are in the non-Eutherian setting, maybe you want that it's proper and finitely presented, but we will come to this later. And then the important property is that P is an ISO outside the image, I mean, outside this closed subset Z. Okay, and then it's the let me give one example that we also discussed yesterday. Yesterday we looked at this nodal curve and the resolution of singularities given by the affine line. So this is a typical example of such an abstract blow-up square. So yesterday we looked at the affine situation. Some of the corresponding diagram of rings. But if you pass to spectra, then this is an abstract blow-up square. Okay, and then it's somehow known. So in general, if you apply K-theory to such an abstract blow-up square, this will not be Cartesian. Okay, so so that's bad because we cannot deduce anything about like the K-theory of this one if we don't know the other corners. And but now, so the idea of this, okay, so CDH descent would basically mean that you send all these abstract blow-up squares to Cartesian squares, and the idea of this post-CDH descent is somehow that you replace this closed subscheme here by something like an infinitesimal tubular neighborhood. So more precisely, you look at the following Zn. This should be the nth infinitesimal thickening. Infinitesimal thickening of Z in X. And then these thickenings form an int scheme, so you can look at Z, which is maybe Z0, and this is a closed subscheme, of course, with always the same underlying topological space, and so on. Zn. Okay, so you have this tower of some closed subschemes. Sorry. Of X, so and you can view the system somehow as an int scheme. So just a formal inverse formal direct system. Zn. Okay, and now the idea is that maybe, okay, if you apply K-theory to this int scheme, Which somehow, if you think of this, this really looks like, I mean, it's not open, but it looks a bit more like something open. So maybe there's a better chance that you get some descent property. And this is in fact true. So now let me formulate this theorem. And I think I need a bit more space. Okay, so let me formulate it here, maybe. And so the result will be that if you pass to the corresponding square here of prospectra, then this will be Cartesian. And let me first of all, okay, okay, maybe I didn't do this in a perfect way. So the first statement, I think, in this setting was proven by you. This is now also not correct. Okay. Oh no. Oh no.
I did surfaces. Okay. Christian has a bunch of papers where he does like threefold with isolated singularities, and you desingularize it, and he said you know that your desingularization looks like a regular blow up and a normalization. Okay. And so he proves the same thing.
Okay. So sorry. Okay. Okay, so this, what should I write now?
And I can't remember who I think it's Krishna Srinivas, it's one paper. Okay. I've got to check. Krishna. I think we do surfaces. Yes. And then there's a bunch of papers, right? And then there's a bunch of papers just by Krishna.
Okay.
I think it's Artin Rees.
Right, it's that. And then Krishna goes Artin Rees papers.
Okay, and Bible also? Okay. Okay. Finally. So, okay, so these are just for surfaces or something, if I understand.
So Krishna Srinivas is surfaces, and then Krishna maybe did threefolds, then he did some other isolated singularity cases.
Okay, let me just say special cases. And then Matthew did the case of some arbitrary schemes of finite type over some base field, but assuming resolution of singularities. And the point is that somehow the method is by using trace method. So using the theorem of Dundas, Goodwin, and McCarthy that the fiber of the trace is truncating. Then you somehow reduce this to a question in TC, and there you have better somehow computational control. And yeah, so this was under the assumption of resolution of singularities, and then Moritz Kertz, Florian Strunk, and myself proved this in the Noetherian setting. And then, okay, let me now first formulate this, and then I will add on this list here. Okay, so this theorem here is assume X is Noetherian. Then the square of prospectra. Okay, let me just write the square. So what do we have? We have K theory of X. Then we have K theory of the somehow X prime. And then we can map to the K theory, of course, so pull back to all these ZNs. So this was an in scheme. So on K theory, this will be a pro system of spectra. And here we get the pro system K of Z prime, also infinitesimal thickenings. We get a square of this. So this is in the pro category of spectra. And this is weakly Cartesian. So let me say what this means, and then so actually you can erase this weakly, but it will come up later anyway. So I introduce it now. So this means i.e. Okay, so you can't. I mean, you can look at this category. So spectra is an infinity category, and pro is just the category of pro objects in this. So this has an internal notion of equivalence and of pullbacks and so on. And but here, so somehow what we proved is not precisely that this thing is the pullback of this corner here in prospectra, but something slightly weaker. Namely, you can somehow form this pullback in prospectra. So you get another thing sitting here, and you get a map from this to this other prospectrum here. And this map is only a weak equivalence, which means that I mean it's okay, after it turns out it is an equivalence, but we proved only it's a weak equivalence, which means that after you truncate the whole diagram, so somehow tau lesser equal to k, of the whole diagram. This is really Cartesian in this category of prospectra for every k. Or you can also say somehow, so in particular, consequent is the map from if you pass two homotopy groups from this guy to the pro groups of this, the homotopy pro groups of this pullback here, this will be an isomorphism of pro abelian groups.
Sorry, shouldn't you say that it's Cartesian in post truncated spectra?
No, I mean that's the same, I guess, because the inclusion of truncated spectra into spectra preserves equivalences.
No, but the fiber product.
The fiber product.
The fiber product, you truncate the fiber product, not the fiber.
Yeah. Okay, maybe this was maybe this was not completely ingenious how I did this. What I mean, you form the pullback and then you truncate this map. Okay, let me write it like this: k of x to pullback. Okay. Now it's going. Thanks. Okay.
Zero. No,
what?
You want it to be zero in prospectra now?
Okay. Thanks. Yeah. Okay. Oh yeah. Is an equivalence? Okay. Now I think it's correct. Any more questions about these notions?
So, like in Artin-Ries or theorems of Grothendieck, is it the case that you have not only equivalence of pro-object, but in the uniform sense, like in Artin-Ries type statements for models? So it is that the kernels will kernel out. There's a fixed constant that to transition maps of zero.
I mean, what you can ask if this is something. Maybe this is similar to saying you could, instead of prospector, you could look somehow at towers and then ask if there's somehow this would be a stronger statement. And actually, I'm not sure. I don't know right now. Okay, but let me comment on this unless there are more questions. So this, yeah.
So what are examples of abstract blow-up squares which are not blow-ups or Milnor squares?
I mean, you can do any. I mean, first of all, not every Milnor square is an abstract blow-up square. These are somehow. I mean, and also if you have an abstract blow-up square of affine things, this doesn't need to be a Milnor square. I will give another affine example later, and then I don't know. I mean, you can do any kind of geometric combination of these things to cook something up. For example, derived blow-up squares. These are not. I mean, if you pass to the underlying classical schemes, these will not be blow-up squares, but still abstract blow-up squares. Okay. So then I wanted to remark that somehow there was more work by Bachmann, Kahn, Ravi, and Sosnilo. So they first of all still X is still a Noetherian, but now it is also allowed to be a stack. So it could be a Noetherian A and S stack. And if you want to know what this is, then you have to ask Bova directly. And then they somehow they removed this weakly condition here. So it's really Cartesian after all. Okay, but
without assuming that X is finite dimensional.
I mean, without. Okay. This I didn't check. Thanks.
I mean, the point is that the diagrams that appear in the projects that you construct actually consist of pro-bounded. They're pro-bounded diagrams, and in this sense, any weak equivalence is automatically strong equivalence.
Okay. So now I want to discuss this Noetherian assumption.
Sorry, I just want to ask a question about this. So is this, in original, the weakly Cartesian, is that the same as this is Cartesian in the prose truncated spectra?
I mean, what do you mean for each? I mean, you could somehow spectra which are bounded above somewhere. It's some. I mean, not uniformly, but somewhere. Not uniformly. Yeah, and then it's the same. Yes. Okay. Okay. Now I wanted to discuss an example about this non-Noetherian setting. So that's the following example that I figured out with Christian Waldhausen. And this is the following. So this is about a non-Noetherian setting. And so we consider following some simple example of an abstract blow-up square, which is affine. So we consider the following ring A. We fix some field, let's say F, and then look at the following version of the coordinate axis. Now we take x and y. So later on we want to divide out by x and y, but what you need is somehow that we make this x divisible by y infinitely often. So we also join variables x over y, x over y squared, and so on. Yeah. So we look at this ring, and then you divide out by x times y. Okay. And then I want to consider the following ideal. So I take the ideal I is the one generated by y, and j is the one generated by x. Okay, and then you see that, okay, now how do I do this? I made somehow y. Okay, let me check that I don't write something stupid here. Yes, so we have j. This should be contained in any power of I. Yeah, that's contained in any power of I, because x is now a multiple of y to the n. So this is contained in any power here. Yeah, so we have this containment and so on, and then this is somehow contained in I. And also we have that j squared is equal to 0, because if you square x, then you get then you can somehow divide once by y. So you can write this as xy times x divided by y. So this is 0. And now I claim that the following is an abstract blow-up square. We look at spectrum of A, and then here the closed immersion defined by this nilpotent ideal J. And here we look at spectrum of A mod I. Yes, like this. So this is also a closed immersion in this case, so it's also proper. Both are also finitely presented in this setting because both are principal ideals. And then we take the pullback here, and what is this? I mean, you just have to compute the tensor product, but because this ideal J is contained in I, this is just A mod I again. Okay, so here's the identity map. And if you look on the complement, this means you have to invert this generator y of I. Then you see this j. I mean, if you invert y here, this will be 0. And so this is also an isomorphism on the complement. Okay. So this is an abstract blow-up square. Now we can check if our what pro CDH would give. So if we had pro CDH descent for this square in this I mean in this meaning, in this form there, then we would get a Cartesian square of pro spectra. So okay, we had k of A maps to k of A mod J, and then here this would go to the pro system k of A, and now we have to take the infinitesimal thickenings here, so this would be k of A mod I to the n. And here we would get the infinitesimal thickenings of this thing, so formally this would be k of A mod I to the n and then plus this j, but j is also contained in all the powers of I, so we can in fact remove this again. And then you see this is now an equivalence. So if this is weakly Cartesian, then this is a weak equivalence. In particular, it's an isomorphism on all progroups, which are just groups in this case. So it's an isomorphism, for example, on K1. So you deduce that K1 of A maps isomorphically to K1 of A mod J. But now, I mean, this is commutative, so the units are a direct summand here. So here we have A star, and here we have A mod J star. And then, but now we observe that this x was nilpotent, so we can just write down a unit 1 plus x, which maps to 1 here, and x is not equal to 0, so this is a contradiction. Okay, so you see this Noetherian assumption is really somehow important to obtain these theorems.
I wonder whether it is eccentric because somehow this thing is not, I mean, regular. I mean, how to say?
I mean, no. I mean, the somehow regularity also in the original thing doesn't play a role. I mean, if you have a regular, so for example, no, okay.
No, I mean, ideal I is not generated by.
Yeah, these are not regular elements. Yes.
Yeah, I mean, this is essentially because that's this sort of, I mean, causal complexity computed is unbound or something.
I mean, if it
because in Noetherian case, I remember there's a asymptotic. I mean.
Yeah, but
I remember.
No, but I mean,
yeah, I think like
let me formulate that. Maybe let me formulate what a true statement is, at least a hopefully true statement, and then maybe this clarifies this question. Okay. I mean, the problem. I mean, maybe you can view it in different ways, but the problem is really the finiteness condition. I mean, this is finitely presented, but it's somehow not. It's not. What in the derived sense not almost finitely presented. Or in other words, if you view this quotient A mod J here as a module over A, it's finitely presented, but it's not pseudo-coherent, and this is what somehow goes wrong. Okay, now let's see if this was a good idea. Okay, so the following, this is now a work in progress, so let me write it in quotation marks as a theorem because it's not completely written down. And this is joint work with Shane Kelly and Shuji Saito. No, here, this was correct. And so this is in progress. There's no guarantee this is really completely correct, but I think so. And the formulation is as follows. So this is formulated for derived schemes because derived schemes somehow show up anyway. So now we let x prime p to x. This is now okay. What is it? It's a proper almost locally almost finitely presented morphism of derived schemes. Derived schemes. And an isomorphism, iso outside. Yeah, also before in this theorem here, for example, you see the scheme structure of this Z doesn't really play a role. It's just the topological space because we go to this prosystem of infinitesimal thickenings anyway. But this is, of course, somehow special to the Noetherian setting. So now I want to say this is an iso outside some closed Z. And here, for the moment, I only consider this, let's say, as a closed subset of the topological space. And there's some finiteness condition, namely with the complement being quasi-compact. No, this was quasi-compact. So in other words, this closed subset can be cut out by finitely, at least local. Okay, let's say in the affine situation by finitely many equations. And now that I say this, I remember that we also need that X is quasi-compact, quasi-separated for reductions to the affine case.
So almost finitely presented on affine pieces, it means something like the pseudo-coherence condition, or?
Yeah, but now these are rings, so somehow. So if this was a finite.
No, I mean you embed, you map to an affine space, so that on the underlying scheme is an embedding. So let us say.
Yes, I think that's.
And then you have a polynomial ring, and then it's a pseudo-coherence.
Yeah. Okay, so you can say you reduce to somehow affine maps, and then. Okay, one way to say is this means that somehow this. Okay, then you have A to A prime. A prime is some A algebra, and this is somehow built up by finitely many cells in each homotopy degree. Somehow, where cell is something coming from a free from a free algebra, something like polynomial algebra, but you need some of those things in higher homotopical degree.
Yeah, but I think that's what he said.
That's yeah. And you can also, I mean, as you can somehow characterize finitely presented algebras classically as compact objects in some category, you can you have a similar characterization of this being almost finitely presented for ring maps in terms of compact objects, namely somehow you truncate. So you have this ring map A to A prime, then you have to truncate A prime in any degree k, and then it's compact in the category of k truncated things. This has to be true for every k. This characterization is actually what is used at some point in this proof. The proof of the theorem that I have not written, namely then the square k of x to k of x prime. And now here's the replacement for this system is just somehow, I mean, it's the same thing, just the notation changed, basically. So you can define something like a formal completion, which you really see as an int-derived scheme here, and the corresponding thing here, x prime completed along z, or I mean the pre-image of z, which is the same thing. This is, and here the weakly spec, weakly Cartesian. Okay, so that's the theorem, and here, I mean, I don't know, maybe someone can again remove this weakly condition, but and I mean, some of the proof really only produces these weakly Cartesian things. So you can also not extend it to arbitrary localizing invariants, only to such invariants somehow which preserve these weak equivalences. So if you have a weak equivalence of pro-derived rings, then you want to apply your localizing invariant and see that it's still a weak equivalence. And this is not, I mean, it's not obvious it's not automatic for general localizing invariants, I think. Okay. Yes? Well, what proper means?
No. I mean, but why do you think proper?
Why you need the properness? Because... No, I don't think so. I mean, then you could just look at I guess as an open subscheme of a scheme, and yeah, okay. I mean, I'm sure one can write down somehow easy counterexamples that you need something like this properness.
So is this special to K-theory or like is there other localizing invariants such that this is true?
Yeah, so it's also okay for THH, TC. Oops, sorry.
Actually, integral TC.
Yes.
That doesn't preserve this connectivity.
Yes, but it decreases it by 1, I think.
No, I mean integrally it has a lot of negative homotopy groups. Like the rational part is bad.
No, because we have the map from K to TC, the first cyclotomic trace. And K preserves, K even increases connectivity. and the fibers, the sk inv, which is somehow infinite connective because it's truncating. So a posteriori TC preserves even increases connectivity by 1, which is somehow surprising.
I mean, it can have a lot of negative homotopy groups, but it doesn't. Maybe
yeah, but I think this doesn't. Yeah.
So here the weakly is for negative homotopy. For negative, it's okay. I mean, the weakly is only for when you.
It's somehow it's really only. I mean, if you truncate in any degree, it doesn't. It's okay. It's really this weakly is really something which only occurs if you look at the full pro system.
What about approximating derived scheme by the truncations? That is the Postnikov tower. That's the.
Yeah, this is precisely what you have to do, and where this comes from. That you need this. That you only get something some weak statement, and that we can only prove something with these somehow localizing invariants which preserve these weak equivalences. Because I mean, this is what comes up in this proof somewhere, that you somehow do an induction over the. I mean, it's not an induction, but roughly you approximate something by these Postnikov towers and do something step by step, and you have to compare the K-theory of, for example, a ring spectrum with the K-theory of a connective ring spectrum with the K-theory of its Postnikov tower.
So what you really need is this approximating fact, like for general localizing invariant.
I'm not sure. I mean, we need this. We need definitely this preservation of weak equivalences. Okay. More questions?
Just to clarify, by K of this formal scheme, you mean choosing your favorite instance?
This is not a formal scheme. This is so how is this?
Or this in scheme, and then you can't extend K theory from there. Is this what you're saying?
This is just an int derived scheme, and then if you apply K theory somehow object rights, you get a pro system. Okay, so this is somehow in the affine situation, if X is spectrum of a derived ring A, and this Z is say cut out by F1 some elements to Fm in pi 0 of A, then this is, so A is now, this is some derived ring, and you can form this Kosohl derived ring, which already appeared in previous talks. So you can form somehow this here, divide out by powers of these elements, Fm to the n. And so previously this was denoted by this derived quotient with this L, and I want to change notation to this double mod symbol. Just not to get confused. And then you take some of the pro system of these. I mean, this corresponding int. I mean, this pro ring. This corresponds to this int scheme.
Yeah, what would have been my favorite?
Good.
But A is not Noetherian, right?
No, it's not Noetherian.
Element of number. The number of elements are finite.
No.
The problem probably comes out.
That's the important condition here. Yeah. Okay. Good. Yeah.
It's finally presented rather than almost finally presented. And you get rid of this.
Yeah. Then yes, but I mean, so being finitely presented is an extremely strong condition, which is usually not satisfied. So it's, for example, I mean, one application that we have in mind for this is proving some generalization of Weibel's conjecture for QCQS schemes.
What conjecture?
Sorry?
What conjecture?
And there's this Weibel vanishing conjecture that the K2 vanishes below negative the dimension. And this holds for QCQS schemes if below negative the valuative dimension. This follows from this result plus geometric arguments, but you need, I mean, the things that you have there are really only almost finitely presented, or locally. You cannot, I mean, somehow finitely presented is too strong. Yeah. Okay.
So when you do blow-ups, so there is this paper of Thomason for usual scheme and regular immersion that computes the K-theory of blow-up, but I suppose for derived schemes, if you, like it was also mentioned in previous talk here, when you use F1, Fn like this, then you have a similar, you do this derived blow up and then a similar calculation of K0 blow up.
Yeah, I will come, if I still have time left at the end, then I will come to this.
So this holds in this case, and then you probably reduce to this such a case.
Yeah, there are somehow two main steps that you have to do. One is somehow this kind of derived blow-ups that you just indicated. And the other one, and this is even, I mean, for derived blow-ups, you can really prove Cartesian, I mean, without the weakly thing. This you can do somehow in the strong sense. Okay, maybe I take this back, but I just now I'm not so sure anymore. Anyway, this is one step, and the other one is somehow pro-excision. So that's the case where this is, let's say, affine and P is a finite map. Okay, yeah. So let me maybe just say I wanted to discuss this as an example, but of course if A is Noetherian, yeah, so X or this A now here. So why do these derived quotients appear and not in this theorem? And this is of course a very classical observation that somehow if you do this derived completion, that's this A mod F to the. Let's just look at one element F in the powers of this. And you look at this pro system, then this is equivalent to the pro system of A mod F to the n. So this is just the ordinary. So let's say A is a Noetherian discrete classical usual ring. Yeah, I mean this is one of these basic observations that of course also enters in the proof of proofs of this theorem here before in some way. And how do you see this? I mean, what are the homotopy groups here? Pi 0 is precisely this one, so this just says, and then there's a pi 1 which is given by the F to the n torsion in A, so this just says that this pro system of F to the n torsions in A vanishes. But this is simply because of the Noetherian condition, so you know that all F power torsion is in fact F to the n torsion for some fixed n. And then you see that some of this transition map in the pro system here, they are given by multiplication by F. So if you do n steps, then every n-fold composite of these transition maps is 0. So you see this pi 1 here vanishes. And it is in fact, then by this argument that Wova said, that you can check this is even an equivalence of pro-derived rings. Okay, good. So this was this example, and then now for the proofs. So all these proofs of this theorem, and also what I mentioned yesterday, the CDH descent for truncating invariants, they all have some geometric input, and then two. There's some geometric input in reductions. Let's say reductions. Which are also not trivial, but I think I cannot say anything about them today. And then there are two facts somehow about K-theory. So one is pro-excision, and the second one is this descent for derived blow-ups. Derived blow-ups. Okay. No. Okay, so now I want to say a little bit about this pro-excision and the derived blow-up case of this theorem and indicate how you prove them. So let's start with pro-excision. And by this I mean this. I mean the case of this theorem where P is a finite map. And you can immediately reduce to the case that X is affine, then everything is affine. And then the ideas there somehow is to use this these excision type results that we discussed yesterday for Milnor squares or pullback squares of ring spectra. And so let me start with the following observation. So if you have such a square that we considered yesterday, A prime, B prime, which is a pullback, now of, let's say, of ring spectra. And you have in addition, you know that this is somehow Tor independent in the sense that if you form the derived tensor product, A prime tensored over A with B, then you have a canonical map to B prime. And if you know that this is an equivalence, so this is a derived tensor product here, and then this immediately implies that that K of the square is Cartesian. Give this a name. Do
you have the Miller condition about surjectivity of one side at least?
It's somehow included in the condition that it's a pullback. You needed it in the connective setting to compare the connective pullback and the actual pullback.
So this is, I mean, this you don't. I mean, if you have a Milnor square, then it is a pullback. But this is more general. You could also have squares where only, I mean, even of discrete rings, where only somehow these two maps are jointly surjective. Or in other words, you have a short exact sequence 0 to A prime plus B, and then to B prime. I mean, for now, for this statement, it doesn't matter. I will apply it later for connective things where also where everything will be connective. But this is just a consequence of this theorem from yesterday.
Okay, this didn't involve this assumption. Okay.
This was for any pullback square of ring spectra. And then it produced this ring that sits inside here, this O dot ring. But we said that the underlying spectrum is just this derived tensor product. So this condition precisely says that this ring in this situation is just the ring B prime. And then this Cartesian square from yesterday just somehow is this square. Okay. Okay, and the idea is somehow to in this setting show that if everything is affine here, that in the pro-sense you precisely have this condition. I mean, that's roughly the strategy. So now let's say the proof of this KST, both KST theorems in the case of for finite P. So you reduce to X is affine. That's easy. Okay, so then everything is affine, and now I need some names. And now I changed I think I changed the names a little bit. So let me say X is now spec A. I changed the roles of B. Do I? Okay, let's see. A spec of A, and let's say this X prime is spec of B. And then you have a finite map phi from A to B. So this is finite. By the way, so finite finite just means, and also proper just means that the underlying map of classical schemes is finite, respectively proper. Okay. So this is now finite, and then it's almost a finite presentation by assumption. And let's say this J is what is J? I mean this closed subset here is cut out by S here by a finite number of elements. And for simplicity, really just for simplicity of notation, let us say it's cut out by one equation. So let's say Z in X is defined by F in pi 0 of A. Okay, and yeah, so then you have the condition that this map here is an isomorphism outside Z. So this means it's an equivalence. This map is an equivalence if we invert this element F here. So let's write J for the fiber of this map phi from A to B, and then this is something one can prove. And this I think okay. It also has to do with this thing that you mentioned before. This is in fact now, how's it called? Almost perfect. Almost perfect. perfect A module as an A module. Oops. Or pseudo-coherent. So in the discrete setting, this would just say that this can be resolved by a complex, by a complex whose terms are finitely generated projective modules, or even finite free, but could be of arbitrary length. And this goes wrong in this example there. Okay. Okay, so then we know that J, and then if we invert this element F, this is 0. These are the assumptions. And now I look at somehow the square of rings that corresponds to these x, x prime, x, and these completions. This is the following, and I claim that it somehow in the pro sense satisfies the assumptions above. So in particular that it's a Pullback square. So now we have A, we have and okay, let me take a bit more space here. So then I can prove this thing also, I hope. So here we have our map phi. And then here we have this pro system, so the completions A mod F to the n. And here you have B mod F to the n, and then this pro system. And I claim this is Cartesian. Actually, it's weakly Cartesian. Sorry. And how do I do this? So this just means on underlying spectra it's weakly Cartesian. So I just compare the fibers. So the fiber here is by different. Okay, let me maybe draw the proof in blue. I mean, is there any difference in colors? So, no. Okay. Let's try, maybe I can just do it with white, but let's try this one. Okay, great. So this is the fiber here, but now the good thing of this derived business, of course, is somehow that everything is exact. So here the fiber is just J mod F to the n. And the claim is, so the claim is, of course, equivalent to this map here being an equivalence, weak equivalence of pro systems. But now, okay, now this means that the fiber of this map is weakly equivalent to 0. So what is the fiber here? I mean, the fiber somehow in every fixed degree of my pro system is just J, right? And the map is given by multiplication by F to the n. And what you see is that the pro system that you have here is the one where J in every degree, but then the transition maps are given by multiplication by F. Okay. And now the argument is in fact a bit similar to this one here. And now we just use the assumption. So this here is 0. Okay. So we have 0 is this J, F inverted. But this we can also write as the sequential colimit, where we take copies of J and then multiplication by F, J, and so on. Okay, so this is 0, and now if this J would be compact, this would already imply that somehow a fixed power of F acts nilpotently on this J here. Okay, this is not quite the case, but at least we know that if we truncate for any k, then we can also write truncation here inside. Oops. Tau less or equal to k of J. And this is still 0, and then you look somewhere at the structure map. Oops. Well, sorry, I have to. Maybe I can change it. Yeah, maybe like this. So you see, I mean, this guy is 0, and so you see that because this one is compact, this one here is compact. This was the finiteness assumption that we have. And this implies that some composite here must be null homotopic. Okay, so this implies that some f to the capital N is null homotopic on this truncation. But this precisely says that if you truncate the upper thing there, then the pro system becomes 0. This precisely means the first one is weakly contractible. So this J pro system with the F multiplication is weakly contractible. Okay. So this proves this claim that the square is weakly Cartesian. And now we have another blackboard here.
Georg?
Yes?
Sorry, is it not true? Because your notion of almost finitely presentability is so finitary, is it not true that you can, somehow after truncation, you can lift it to an Noetherian approximation of your scheme? So if you have an Noetherian approximation of x, is it not true that you can lift x prime to this Noetherian approximation and somehow reduce this theorem to the previous?
So if in the Noetherian case you prove it with fixed bounds, then you can pass the limit. But I suppose...
Ja, maar dat biedt baseline te duidelijk.
I mean, okay, I cannot answer now, unfortunately. I mean, there's some theory of Noetherian approximation, that's true. And this is also, I mean, I use something like this somewhere, but not for just simply somehow reducing the complete statement. I mean, I don't know, maybe it's possible.
I don't know, just a wishful thinking question, so it might be completely incorrect.
Yeah. It's okay, right now it's not clear to me, I don't know. Okay, but now we have now the situation that we have a pullback square, and then we just know that in this particular case, okay, let me also do it like this. Also, this other condition that we had here in this node, this is automatically satisfied because now, I mean, by definition, this b mod f to the n is just the tensor product of the other things. So this is automatic. And plus okay, how did I write b tensored over a with this a mod f to the n? This is equivalent to b mod f to the n, and then you can put this together with this theorem from last time. So you have to do a little. I mean, of course, this theorem is really for pullback squares, not for pro systems or so. But what you do is you replace this a here by the pullback of this square, and then you know that this is still then it's a pullback square. It's still connective because these maps are surjections on pi 0, and this map here, the upper one that you get from A to the pullback, this is a weak equivalence, as this follows from what we proved here. And then you apply this theorem to this. So this these things together imply this finite case. Okay. Good. Okay, now let me. 5 minutes left. Okay.
So here the possibility truncation appear. I mean, you have to know that for a fixed range of K groups, let's say less than or equal to n, you can replace the ring by some.
Yes. Yeah. That's true, and this follows this follows from the. I mean, that K theory has this property follows from the plus construction description. So using BGL, basically you can explicitly see that K theory increases even connectivity by 1. Okay, let's maybe this one here. I have 20 minutes. Ah, yeah, okay. This is this. Okay.
Only if it's a long one.
Okay, good. So then the second input is somehow is these derived blow-ups. So descent for derived blow-ups. And now let me recall this theorem of Thomason that was mentioned before. So let's say so this is somehow the idea. So Thomason proved that if you have a blow-up in a regular center, then you can look at this blow-up square that you get, and this is even Cartesian. I mean, K theory of this is even Cartesian, and this works for any localizing invariant. So let me recall this. So R is a ring. So commutative now, of course. I mean, it's actually all the rings today, I think. Then T1 to Tm is a regular sequence. And then we look at the following situation. Let's say Z is a closed subscheme, which is defined by these elements so T1 to Tm of X, which is spec of this ring R. And then we blow up X in the center Z here. So let's denote this by X tilde to save some notation. This is the blow up of X in Z. And then we have the exceptional divisor E, or actually, okay, let's call it E.
Below ZX. What? Notation is not. I think usually it's below Z of X, but maybe not.
Yeah, I'm also I don't know what the standard is, so my co-authors use both things. I mean, and then so I could choose, and now I choose this one because it's easier if you want to. Actually, maybe it doesn't matter, but I thought it's good if I have more space here, because if you have additional indices that you put here in the index, then it's not so nice anymore. So this was my reason for writing it like this. But if the other one is standard, then okay, that's good to know. Thanks. Okay, so this is again now a Cartesian square of schemes. So this is that's a Cartesian square of schemes, but it's not derived Cartesian in general, at least. Okay, and then the theorem of Thomason is that the square here gives a pullback square on K theory or any localizing invariant. I mean, he formulated it for K theory, but the proof works in general to K of X tilde, to K of Z, and to K of E. This is Cartesian. Yeah, and somehow the rough idea is to obtain a derived version of this one. And of course the geometric input that you use for these proofs is that then somehow you can in some sense build up every abstract blow-up square from such derived blow-ups, which I didn't define so far, but this just means you take such a blow-up, an ordinary blow-up in a regular center, and then you take a derived pullback. And these finite maps that appear there. Okay. So he proved that this is Cartesian, and let me just sketch what the main ingredient is here. So the point is that you can somehow you understand the category of perfect complexes on this X tilde more or less explicitly. I mean, you have a very good understanding of this category of perfect complexes. Namely, this is as follows. So there's a filtration. So let's write it maybe here or here. So we have the perfect complexes on the blow-up, and now I took m equations. So this has a filtration which stops, I think, in degree m-1. So that's this p lower dot will be my finite filtration by stable subcategories. Blah 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 blah. And then here somewhere is PL, let's say. So now I define this. What is the else step of this filtration? So first of all, you look at this thick subcategory, thick stable subcategory that's generated by the following sheaf. So it takes the structure sheaf, and then okay, here we have this inclusion of the exceptional divisor, this J, and you take J lowers the push forward, derived push forward of the structure sheaf of the exceptional divisor, and then you twist by minus k, and then k. Okay, now I don't have enough space probably. K is from 1 to L. Okay. So you look at this thick subcategory generated by OX, the structure sheaf, and then these twists of the structure sheaf of the exceptional divisor where k runs from 1 to L. So it starts with somewhere P0, which is just generated by OX tilde, but just by the structure sheaf. Okay, we have this finite filtration here. And then you check that you have, of course, the pullback along this blow-up map P here, this projection, from perf of X. And then, I mean, these are somehow some more or less easy cohomology computations that this is fully faithful, and by definition, its essential image is this P0.
So this is the affine. Okay.
Yeah, it's affine. Yeah.
And the sixth subcategory, you add direct summons always.
Yes. Yeah. And then for the higher ones, what you check is that the subquotients P. Okay, how should I write this? Yeah, okay, let me write it like this. And we also can take something in a perfect complex on Z. Then I need more notations here. Let's call this map here Q, the map from the exceptional divisor. We can. Okay, let's see. What do? We pull back with Q, then we push forward with J, and then we twist by minus L, I guess, and view this as a functor to PL, and then mod out by PL minus 1, so to this subquotient. And then again one computes that this is also an equivalence. Okay, so we understand all these subquotients, and in fact, similarly, for the exceptional divisor itself. This also has a similar filtration, and the subquotients, I mean, then somehow the base thing is perf of Z, and the higher subquotients that appear are also equivalent to perf of Z. And from this you read off the result. Okay, so this gives the result. So that's the end of the sketch of this proof. Yeah, because then somehow you see that. Let me say one more word. I mean, now you have this filtration, so you can always get from one step of the filtration to the next, and then you have a Verdier quotient or Karoubi quotient. And you compare this for the blow-up X tilde and for this exceptional divisor. And the map on these co-fibers, they are always equivalences, because all are equivalent to perf of Z. And then from this you deduce this theorem. Okay. So now I have 10 minutes left. Okay, so now we do the same somehow for derived blow-ups. So now, let's say now X could be any let's say derived scheme, and it's. So I mean, so there's a more advanced theory of derived blow-ups that was developed mainly by Adil Khan, but this I only do a somehow very naive approach here. So let's see. Let's say this comes equipped with a map f from X to the affine space. Or in other words, again, so over the integers. So this is just m elements in pi0 of this ring. So this in particular defines a zero locus here of these functions. And this I want to blow up somehow. Yes. Why this is an equivalence? I mean, yeah, this is some. I mean, first of all, it's again from the definitions. It's more or less easy to see that this will be essentially surjective. The only thing what remains here is the J lower star of this OE twist minus L, which is precisely in the image here. It's the image of the generator here. And then, then it's some cohomology computation that this is fully faithful also. Okay, but I mean, for example, for the exceptional divisor itself, that's just a projective space, and this really comes down to the classical computation of the cohomology of the twist sheaves on the projective space. Okay, now we have a derived scheme which is equipped with such with a morphism to AM, and then we define the derived blow up. Okay, so definition maybe. So the derived blow up of X in F. Let me write it like this is, and what you do is you just take. Let's denote it by X tilde again now. You just take the blow up of, so by this you should think of F defining a zero locus, right, in your scheme, and this you want to blow up in a derived way. What you do is to just look at the usual blow up here of the origin. So the blow up of, okay, what was my notation with this? Of the origin, and then you take the pullback along this map to X, but now you do a derived blow up here. Derived pullback. Yeah. So maybe let me write a little R here for derived. Just if I forget this. Okay, maybe let's take this on. Yeah, this is a good comment. Yes, thanks. I actually wanted to say the same thing, but no, I forgot. Yeah.
Affine space is the usual affine space.
Yeah, it's somehow discrete affine space over the integers. Okay, so that's the derived blow-up, and then we define the derived exceptional divisors and also thickenings as follows. So first of all, it's maybe still part of the definition. I write Z and then brackets N to denote. Okay, no, let me say. How do I say this now? Sorry. Okay, let me first of all define Z, which is the vanishing set somehow of F, which is more precisely the vanishing set of F1 to. I mean, really think of this map F as M functions. So this is by definition just similarly the derived pullback of A to the M of the origin. So in other words, this if X is affine, this thing is precisely this causal. It's represented by this causal derived ring where you mod out by F1 to Fm. And then now I can define some more thickenings. Zn, and using this notation, this would be F1 to the n, Fm to the n. And then we need some more thickenings of the corresponding exceptional divisors. these are simply defined again by the pullback in derived schemes. So that's the pullback in derived schemes of Zn maps to x, and then this blow up x tilde. Okay. Yeah. D of n. So these squares are all derived Cartesian. So it's a bit different than in Thomason setting, because in Thomason setting this square was not derived Cartesian. Okay, and then the theorem is the following. So there's somehow again the weak version. This was part of this paper with where is it? That is gone already. The no, here it is. Of this paper. And then, so later, Ben Antio found in fact a simplification of the proof, which also shows a stronger statement. So Antio, and this says the following. So if you look at the square k of x, then k of x tilde, and then here this prosystem k of Zn and k of dn. This is Cartesian. Okay.
So if you define dn instead of defined by f to the n, just as the derived pullback of the thickening of the exceptional divisor in the blow or fine space, then this will be closer to the previous iteration. So in this case, you should have Cartesian for a fixed n.
No. No. but so first of all, I mean, this is what we actually did in this paper. And what is true is if you fix this x, this one blow up, and then you look you just have the z. I mean z0. Yeah. I mean for your fixed n equals not 0, n equals 1. It's true, but it's no longer true if you go 2 powers. But somewhere in the pro sense, it's all in the pro sense. All these things then are the same.
Because the blow up is not the same.
Yes.
The blow up is not the same.
Yeah. Yeah. But
it's like a Petri-Hall principle, right? And somehow you can.
Can you say?
I mean, you have a power, and you can squeeze it into this causal type. Just a comment to your pro.
Yeah. I'm not completely sure if I understand correctly what I mean, but probably it's.
For n equal 1, what I said is correct.
Yes, it's correct. Yeah.
And this is the part of the proof in your work.
Yes, this we used here, but at the end somehow we deduced also this statement, and then Ben Antio somehow gave a nice short argument for this statement, which also proves really that it's Cartesian, and we only proved this weakly Cartesian version here. And okay, but somehow my time is almost up. Then let me maybe just say what the argument is. It's the, okay, we have this, let me just get this down a little bit. Okay, so the point is, in principle you do the same as what Thomason did, and you start somehow with the category of perfect complexes on this x tilde has a similar filtration as here, because you just pull it back, the one that you have in the regular setting. And then because this dn is now defined as the derived pullback, you know that the category of perfect complexes here is somehow, it's just the somehow tensor product of the categories of perfect complexes here and here over the perfect complexes here. So in particular, you can somehow take this filtration that you have and pull it back further to this dn. And then you see this becomes a very simple question, and at the end just boils down again to something like this vanishing of Kosul homology. So then you let me leave it like this. So it's this kind of reduction. You pull back this filtration, and then this reduces to one simple computation, which is similar to what we've done before. Okay, so let me stop here. Thank you very much for the attention.
Any questions? Further questions? Yes.
So this projection falls for ring spectra, right?
Yeah, if I formulated it correctly, I think yes. Yeah.
My question was if we.
I mean, we need so at least so connectivity and so on is important.
Okay, but my question was if we can do it for spectral schemes, not derived schemes.
I think probably yes.
Sorry, how do you make sense of this modular?
Yeah, that's the point. But I think you can probably.
No, I mean sphere spectrum in mod 2. I mean it's very bad.
Yeah, no. Of course, this does make sense. But still, there's a notion of completion of spectral schemes, but I've not checked, or I didn't think about it too much. Whether you could make sense of this completion somehow in the pro sense, at least on. It seems like the people in the last row.
I think you can. There is an analog of that statement about derived rings that you can somehow approximate these quotients with the derived quotients, but in the spectral sense. There is a statement in spectral irregularity about that. And then somehow everything goes through, but you really have a weak Kullback square, not a strong Kullback square.
Yeah.
So in the right scales, usually.
Sorry, but for grow-ups, it's not clear how. It was not clear for me how to generalize.
Yeah, it's also not clear to me. Maybe I don't know. Maybe Adil can't.
I think paper of Adil can't.
It's also possible. Okay. Okay, thanks.
So I think in derived schemes they start from simplicial rings, so you have only a non-negative homotopy. So is it possible like to look at ring spectra over HZ or something which is like, and do something with lower negative homotopy? I mean,
I don't know. I mean, as soon as you have something non-connective, so with non-vanishing negative homotopy groups appearing, then I think all these methods do not work anymore because we don't know that K-theory still preserves these weak equivalences. So this is really something about K-theory of connective ring spectra, because or simplicial rings or whatever, because there you have this description via the plus construction. And you don't have this for non-connective ring spectra, so I don't know. So I definitely don't know how to control this.
So I wonder if we replace with this pro scheme with this Tamme space of the Konova bundle, this would also work as a tubular neighborhood. I mean, to have some results for this.
I don't know. Sorry.
Anything further?
It seems that your proof works as long as like in the case K is replaced by some other localizing invariant that has that truncation property.
What do you mean by truncation property?
Like K of the.
So that somehow that K theory or E theory in a certain degree only depends on. Yeah, that's true. So this is why I wrote somewhere. For example, it's true it holds for THH and TC and so on. Yes.
If there's nothing further, then let's thank Georg for his mini course.